For our last video on thermodynamics, we're going to be talking about the second law of thermodynamics and then heat engine. The second law can be stated a couple different ways. One is that heat flows from hot to cold. Another way it's stated, and this is what you might see more often, is that the entropy for a closed system tends to increase. Okay, entropy is disorder. You should remember that from chemistry. They actually mean the same thing. You don't have to draw this, but if I have a situation where I have hot at one end and cold at the other end, that's a type of order. If I told people to line up from shortest to tallest, that's in order. Here the temperatures are lined up from hot to cold, that's in order. So if I want disorder to happen, the heat is going to flow down this way, and you're going to end up with a uniform bar in terms of temperature. So that's why we're the same. As a complete aside, sometimes you'll hear the second law used to refute evolution, because they'll say that we started out with single-celled organisms and eventually built more and more complex organisms. That's a decrease in entropy, therefore evolution can't be true. Now, whether or not you believe in evolution, that is a bad argument. Here's why. Okay, we are not closed systems. We are getting energy from the sun, and that energy can be used to build more complex organisms. The whole system, if we consider the sun and the earth, heat is flowing out of the sun to the earth. So for the whole system, entropy is decreasing, even if, because life is getting more complex, for this little part of it, entropy is increasing. So, anyway, entropy tends to increase for a closed system. Now, heat engines. A heat engine, our description is going to be this. A heat engine takes energy from a hot reservoir. Okay, the energy it takes is going to be QH. That's the energy, the heat energy it takes from the hot reservoir. It uses the energy to do work, which is W, and exhausts some energy to a cold reservoir, and the energy it exhausts, we're going to call it QC. Now, a diagram for this, and I think it actually helps to draw this diagram kind of every time you see one of these problems, is this. Okay, here is our engine. You have a hot reservoir. You take energy from it, QH, use that energy to do useful work, and then exhaust some energy to our cold reservoir. Now, if we put this together, you can kind of see that the energy coming in is going to equal the work done plus the energy going out. So let's say I had 500 energy coming in, I was able to do 400 joules of work with it. How much would I be exhausting? The rest. I'd be exhausting 100 out. So it always is going to balance like that. And actually, let's space for this down here. So that is the work and energy relationship. The next thing is the efficiency. How efficient is the engine? Well, if I was taking in up here at Q hot, if I was taking in 1,000 and I was only doing 100 worth of work and then exhausting 900, that's not very efficient. I'm only getting 100 useful work while I'm trying to use 1,000. But if I got 900 work out of the 1,000, that would be a lot more efficient. That would be 90% efficient. So efficiency, we can calculate by doing the work done divided by QH. Now, sometimes you won't see it in terms of QH. You can also just kind of think of that as being the work done divided by the energy that you're putting in. Okay, so at the top of the next page, we have an example of that. Okay, I have an engine that takes in 12,000 joules, exhausts 8,000. How much work is done? Okay, so like I said, I think it helps to draw this picture every time. So it takes in 12,000. So we got QH coming in is 12,000. We're going to do some work with it and then exhaust some energy. Now, it says I'm exhausting 8,000, so that's QC. So this is going to be 8,000 joules, right? And then it says how much work is done and how efficient. So it's actually going to be easier to find the work done first. This is really straightforward. I have 12,000 coming in. I exhaust 8,000. How much went into doing work? So the work, 12,000 minus 8,000 is 4,000 joules. All right? And then for our efficiency, it's the work divided by the energy in. So it's going to be 4,000 out of 12,000, which is 0.33 repeating, or 33%. Next, heat pumps. Heat pumps are heat engines in reverse. So what happens in those is they take energy from a cold reservoir to work on it and exhaust energy to the hot reservoir. All right, so it would kind of look like this. Here is my heat pump. Okay, so I take energy from the cold reservoir, I do work on it, and they exhaust the energy into the hot reservoir. Now, the energy doesn't want to go that way. Energy doesn't want to go from cold to hot, so you have to do work on it, and you have to put a lot of energy into these in order to make it work. But an example of this would be an air conditioner. Okay, it might be 70 degrees in the room and 85 outside, and it's actually taking heat and pumping it from the 70-degree room into the 98 degrees. Another example is a refrigerator. So they use a lot of energy because you're pushing the heat in a direction it doesn't want to go. Now, an ideal or Carnot engine, okay, a definition, is that Carnot engines are perfectly reversible. Doesn't mean you have to reverse it, okay? But they could be perfectly reversed, okay? So that no energy would be lost. Now, that's an ideal. Okay, this is actually impossible. Okay, because there's always going to be some energy loss from friction. But what you would do is you would take your heat engine, okay, like this one up here, all right, and take energy in, do some work with it, and then exhaust some energy, then you could turn around and take that energy you exhausted and put it back into the engine, which is now like a heat pump, do work on it, and get the exact same energy back. But again, that is actually impossible. So, the Carnot efficiency is calculated this way. Okay? Instead of QH minus QC over QH, that's actually the same equation, right? Because QH minus QC is work. So we have work on top divided by the energy in. But what you can do with a Carnot engine is replace the Q's with T's, the temperature. The reason why this is easier is because it's hard to measure exactly how much energy is going in and out. It's hard to measure Q. It's easy to measure temperatures. So it's a lot easier to measure this. However, this is going to give you like an upper limit. It's actually impossible for one to be this efficient. But it would give you an upper limit as to how efficient it can be. So here's an example. An engine takes energy from a hot reservoir and exhausts to the environment at 20 degrees Celsius with an efficiency of 20%. What is the temperature of the hot reservoir? So again, I kind of like to draw this. But the diagram is going to look a little bit different. Okay, we have the hot reservoir at some temperature TH. We're going to take some energy out of that reservoir, do some work, exhaust it to the cold reservoir. This is some temperature TC. Okay, now we're fine that the efficiency is 20%. So we'll use this new Carnot engine. Okay, efficiency of the Carnot engine is TH minus TC over TH. Right? Now, we can replace the EC with 20%. So 0.2 equals. We're trying to find the temperature of the hot reservoir. We don't know that. The temperature of the cold reservoir is 20 degrees Celsius. These are T's, not delta T, so I can convert that. So that's 293 Kelvin divided by pH. Now, if I cross multiply, this becomes 0.2 TH equals TH minus 293. Okay, if I subtract 0.2 TH from each side, I get 0 on this side equals 0.8 TH minus 293. 293 is 0.8 TH. Just added 293 to both sides. And then TH equals 366 Kelvin. So if the actual, all right, would have less than the 20% efficiency, again, that's the upper limit because it's Carnot efficiency. We have one more example at the top of the next page. If we have an ideal engine that's hot reservoir at 1600, a cool reservoir at 20, we want to know the maximum efficiency. And then at part B, we're given how much energy it takes in, and we want to find the work done. So again, like I said, I like to draw these. So here's my engine. We have the hot reservoir. Is at 1600 degrees Celsius, so that would be 1873 Kelvin. Okay, it's going to take energy in QH, do some work, and then exhaust some energy, QC. And we have the cold reservoir with a temperature of 20 Celsius, which is 293 Kelvin. Okay. Now, we want to find the efficiency. So the Carnot efficiency is TH minus TC over TH. That's 1873 minus 293 divided by 1873. That's going to give 1580 or 1873, which is 0.84 or 84% efficient. That was part A. Part B, okay, now it's telling us that it takes in 20,000. So I know this is 20,000. And I want to know how much work is done and how much is exhausted. So I'm going to take this efficiency, use that to find the work done. So 0.84 equals work over, and our QH was 20,000. Okay, and when I cross multiply, I will get that the work is equal to 16,800 joules. So I can even write that on my diagram. It's 16,800 joules. Then I want to find how much energy is exhausted, QC. Well, I took in 20,000, did 16,800 work. How much is left to be exhausted? It's just the difference. So QC is going to be 20,000 minus 16,800, which gives me a value of 3,200